Now let's recap with irrational numbers, because we're going to discuss about how we can identify a number to be irrational or rational, supporting through some of the theorems and properties which we're going to discuss out here. So before that, an irrational number is a number which is not rational, is how we understood the concept when discussed with the different types of numbers in real number system. So the numbers which are not rational, that is, the numbers which cannot be expressed in the form p by q, where p and q are integers and q not equal to 0, are called the irrational numbers. So mathematically, the irrational numbers are denoted with all real numbers except q, because we don't have the rational numbers included in the irrational part. So excluding this, the remaining numbers in the real number system are called the irrational numbers. So coming to the irrational numbers, there are many example irrational numbers which we can discuss here, like root 2, root 3, root 5, root 7, etc. And root of a prime number is an irrational number, and pi, which we know, is an exceptional irrational number because this has its own history in mathematics. Then you can also take 0.0101110, etc. So I have different types of irrational numbers in mathematics. This being one of the case is how I understand the irrational numbers. Now let's see how we can identify a number to be irrational. Why do I call root 2 to be irrational number? There should be a mathematical proof valid for that. So is what we're going to discuss in today's session. So before that, there is a very important theorem which connects the fundamental theorem of arithmetic, and let's see what the statement says for the theorem. So if I consider the theorem which says that let P be any prime number if that prime P divides a square and a belongs to positive integers, z plus is positive integers. If P divides a square and a belongs to positive integer, then P divides a. This is a very important theorem which is helpful in identifying a number to be irrational or not an irrational number. And the statement, when I read it, says that for any prime number p, if p divides a square, for a being a positive integer, then p must divide a, is how I understand the statement of the theorem. So to go with a small short note on the proof of this theorem, let me start with the proof, where I take let p be any prime number. Then let a belong to z plus is what I have considered here for this positive integer, such that we have already discussed in the prime factorization method the fundamental theorem of arithmetic, which stated that every number can be expressed as product of distinct or not distinct primes. It can repeat, but it should have product of all primes. So going by the fundamental theorem, such that by fundamental theorem of arithmetic, a can be expressed as product of p1 times p2 times p3, so on and so forth, pn minus 1 times pn, the product of different primes, where each of this need not be distinct because some factors repeat, where p1, p2, p3, pn minus 1, pn are distinct need not be 2. So these primes are distinct or may not be distinct because sometimes they repeat. So are distinct or need not be distinct primes. So for these different primes, I have A which can be expressed as P1 times P2 times P3, so on and so forth till Pn. Now using this, my statement says that if P divides A square, so let P divide A square. Divides is the symbol which I use as a sign as a straight line. So this symbol indicates that P divides A square. That implies P divides A square, which can be written as P1, P2, Pn whole square. So because A is P1, P2 till Pn, I square it to get this. That implies P divides P1 square, P2 square till Pn square. So P divides this. So as you can see here, I have considered the case where P divides A square. Now because A square is P1 times P2 times P3 till Pn, therefore that implies that P is one of the factor of A square. Now when I say a number divides another number, that number is said to be one of the factor of the given number. So if I say A divides B, A is one of the factor of B. Therefore P divides A square implies P is one of the factor of A square. But A square is already with different factors P1, P3 till Pn. Therefore this P must be one of the P1, P2, P3 or Pn. When I take the square separated. So when I substitute here, since P is one of the factor of A square, that implies P is one of the factor of P1, P2 till Pn. But P1, P2 till Pn are all possible factors of A square. That implies all possible factors of A square are P1 to Pn. It cannot have anything other than that. But when I say that P is one of the factor of A square, that means P should be one among P1 to Pn, because these are the only factors available in A square. Therefore, which concludes that P is one of either P1 or either P2 or either P3 or either Pn. Therefore, P should be one of them. That implies when one of them is P out of these, which is nothing but A, when multiplied becomes A, that means P must divide A because P lies in one of these products. If it lies somewhere in between, then this clearly indicates that P divides A because P is one of the factor in A. A expressed in the form P1, P2, P3 till Pn is how we understand the concept of division and the factors. So P is one of this. That implies A equal to P1 times P2 times P3 so on till Pn continued here implies that P divides clearly A because P is one of P1, P2, P3. So it must lie in between either P1 to Pn, somewhere in between. Therefore, P divides A. Therefore, the proof. So P divides A is what we get in the statement. Therefore, when I consider any prime number such that if P divides A square for any positive integer A, then immediately I can conclude that P divides A. And this is one of the most important theorem which supports and helps us in identifying a number to be rational or irrational. So let's use the previous theorem which we have discussed through an exclusive proof and find whether the given number is a rational or an irrational number. But before I proceed with this problem, let's understand that there are some proofs which are proved by contradiction. Let's say, for example, if I wanted to show that root 2 is irrational, I take the assumption that root 2 is rational, and then finally I come to a contradiction, and that contradiction, mathematically valid, will make me understand that the root 2 is not rational, but it should be actually irrational. Such kind of proofs are called proof by contradiction and are very much supported in mathematics, and let's see how we can do this using proof by contradiction for identifying root 2 to be an irrational number. So my question here says that prove that root 2 is irrational. So I wanted to prove that root 2 is an irrational number. So when I wanted to prove that root 2 is irrational, I go by contradiction, as we already discussed. So what is the contradiction of irrational? Rational. So my assumption here starts with let root 2 be a rational number. To follow with the rest of the proof, I consider root 2 to be a rational number. That implies root 2, if it is a rational number, by definition of a rational number, it can be expressed in the form P over Q. So this can be expressed in the form P over Q such that P and Q are integers and Q is not equal to 0, is how I understand the rational number. So therefore, root 2 can be expressed as P by Q in the form with each of them being integers and denominator not equal to 0. Now here, if P and Q have common factors, then those common factors can be simplified or cancelled, then I get the most simplified form. So let me take the most simplified form of P by Q as some A over B. So here, so if P and Q have common factors, then it gets reduced to another form as, say, A over B, such that whenever the answer is in most simplified form, then we say that these two are co-primes. The HCF of these two numbers would always be 1, or there's only one common factor, that is 1, between A and B. So when I take this, A and B are co-primes. Indirectly, we identify the co-primes by taking HCF of AB is 1. There's only one common factor, that is 1. The highest common factor is 1. So when I just get it in the most simplified form, I get root 2 is A over B. So that I simplify this by getting this as A is root 2 of B when I cross multiply them. Then this on squaring on both sides gives me A square is equal to root 2B whole square. By squaring on both sides gives me A square is 2 times B square. When I just simplify this with a root 2 whole square is 2 and B square is B square, so that I get this. Now, therefore, A square equal to 2B square implies A square implies this 2 is set to divide A square, because clearly A square can be expressed as 2 times of B square, such that when I have 2 as one of the factor of A square, so 2 divides A square, that implies 2 divides A by the previous theorem which we have considered as in the previous case. So using the previous theorem, when 2 divides A square, then immediately I have P divides A, because P is equal to 2 is a prime. So 2 divides A, as supported by the previous theorem which we have already discussed recently. So when I have 2 divides A, that implies A can be written as 2 times of some C, because when 2 divides A can be expressed as multiple of 2, or 2 is one of the factor. Therefore, I can have 2 times multiplied with some c, where c is some integer, a positive integer. So taking this into case, that implies a is equal to 2c. That implies when I square this, I get this as a square is equal to 2c whole square when squaring on both sides, such that this gets reduced to a square equal to 4c square. That implies a square, which is already 2b square, can be substituted in place of a square as 2b square out here. So a square being 2b square is 4c square. Now here, this is nothing but b square is 2 1s, 2 2s, 2c square. So when I take 2 to the right, I get b square equal to 2c square, is what I obtain by substituting in place of a square. Now similarly, as I proceeded here, I see that b squared can be expressed as 2 times of c square. Now because this is a multiple of 2 in the right hand side, that implies that this 2 clearly divides b square, as can be seen here. B square is 2 times of c square. Therefore 2 divides b square. That implies, by taking the previous theorem, I get 2 divides b. So I get 2 divides b is what I conclude in the previous thing. That implies I take 2 divides a and 2 divides b. That implies when I compare these two, 2 divides a and 2 divides b, that implies 2 is the common factor of a and b. So 2 is dividing a and 2 is dividing b makes me clearly understand that 2 is the common factor for both a and b, which is not possible because a and b are co-primes. But this is a contradiction because a and b are co-primes. They don't have anything common except 1, which contradicts the statement. But this is a contradiction as a and b are co-primes. As you can see here, but this is a contradiction as a and b are co-primes. Therefore, this contradiction makes me understand that the proof by contradiction is that if this is a contradiction, our assumption is not correct. That implies, therefore, our assumption that root 2 is a rational number is wrong. Our assumption is wrong, and therefore, by contradiction, therefore, by proof by contradiction, root 2 is not a rational number. Root 2 is an irrational number. Therefore, root 2 is an irrational number. So the proof by contradiction is how we see here. Therefore, we finally conclude in mathematics that the root 2, which we generally take in many of the problems, is not a rational number, but is strictly an irrational number. It cannot be expressed in the form p by q, where p and q are integers and q is not equal to 0, thus an irrational number. So now let's take a different example problem and prove whether it's rational or irrational. So for example, I take here, prove that 7 minus root 2 is an irrational number. I want to prove that 7 minus root 2 is an irrational number. Then how do I do that? So in this case, again, I go with the proof by contradiction. So because I want to prove that this is an irrational number, I consider that it is rational, then I prove that my assumption is wrong, and finally I get that this is an irrational number. the proof by contradiction. So let 7 minus root 2 be a rational number. So therefore, because this is a rational number, as in case of the previous problem, we take this in the form of a by b, where a and b are coprimes. Now, further simplifying this, I get this to be 7 minus a over b, which on further simplification gives me root 2 is equal to 7b minus a by b, which on taking LCM further simplifies to 7b minus a over b. Now, as I can see the right hand side of this equation, clearly I see that since a comma b belong to z plus, because of course there are positive integers, this being rational numbers, therefore and b are also positive integers, the sum and difference. So these two are being positive integers, and because b is not equal to 0, the case here says that this is also a rational number and b is not equal to 0. Therefore, by definition, 7b minus a over b is a rational number. This is clearly from the two conditions which this right hand side holds, where 7b minus a and b are positive integers and b is not equal to 0. Therefore, this fraction must be a rational number. But whole of this fraction is equal to root 2. That implies this being equal to root 2 is also a rational number. But this is a contradiction. This is a contradiction because root 2 is already proved to be an irrational number in the previous problem. So, since root 2 is clearly an irrational number. Now, since root 2 is clearly an irrational number, therefore, by proof by contradiction, seven minus root 2 is an irrational number. My assumption is wrong. Therefore, this is an irrational number, is how I conclude the statement. Therefore, when I take the note, the sum or difference, in this case of this problem being difference or difference of a rational number and an irrational number is finally concluded to be irrational. The difference of this being irrational, where one of them is rational and one of them is irrational, the statement concludes that the sum or difference of a rational number and an irrational number is irrational always. Similarly, I have the second note which says that the product of a rational and an irrational is also irrational. Therefore, if I take the examples like 3 root 2, 7 root 3, 4 root 5, etc. are all examples of irrational numbers because they are in the product of rational and irrational, rational and irrational, rational and irrational. In that product combination, they form an irrational number, are the two properties which are important connecting the irrational numbers with the rational numbers. Now that we have seen the rational and irrational numbers connected to the sum or difference and product as seen with these two properties. Let's see the third property, which states that the sum or difference of two irrational numbers is irrational or irrational. So what could that answer be out here? The sum or difference of two irrational numbers is rational, or it can also be irrational. Both the cases are possible. So when does two irrational numbers when added give a rational number is the most interesting property, which we are going to support with the examples. So let's see where we consider two irrational numbers and we add or subtract to get a rational number. Is it possible? Yes, it is possible. Say for example, I take a is equal to root 7 and b equal to negative root 7, so that when I add these two, I get root 7 plus minus root 7, which on simplification gives me 0. So a and b are rational numbers because root 7 and negative root 7 are irrational numbers, and then when I add them I get 0. 0 is a rational number. Therefore my statement, which states that the sum or difference of two irrational numbers is either rational or irrational. Rational is possible in case of this property. So now that we have discussed about rational and irrational numbers connected through the properties of addition, subtraction and multiplication, we will try to see the different properties which the real numbers hold in mathematical system. As we already discussed about closure, commutative, associative, identity and inverse in the previous sessions, let's start with how the real numbers hold. So for any a, b, c belonging to the real numbers, I have the following properties which hold in case of the properties of identity. So the first property I identify as closure, then the next is commutative, and the next property I identify as associative property, then existence of identity, and then the existence of inverse are the 5 properties. And finally we have the distributive property, which connects more than one binary operation. So under these 6 properties, let's see what the real numbers hold in case of, say, first addition and then multiplication, because addition and multiplication are the only binary operations which we generally consider in operating the real number system. Subtraction is understood as indirectly with addition, because 5 minus 3 I can write it as 5 plus of minus 3. Similarly with division, which is understood in the concept of multiplication, 5 over 3 is understood as 5 multiplied with 1 over 3. So therefore addition and multiplication form the base in understanding all the 4 binary operations, plus, minus, multiplication and division. So to start with closure, we all know that the closure property for any 3 numbers a, b, c is that a plus b also belongs to the real numbers and a into b belongs to the real numbers in case of multiplication here, in case of addition here. So closure property states that if a and b are any real numbers, the sum is also a real number and product is also a real number, respectively, for addition and multiplication. Similarly, my commutative property says that a plus b is always equal to b plus a. A times b is always equal to b times a. My associative property says that a plus b plus c is a plus b plus c. A times b times c is a times b times C is how I understand the associative property. Then identity property says that A plus 0 is A is 0 plus A, which is called the additive identity. Here 0 is said to be the additive identity. Now in case of multiplication, A times 1 is A is 1 times of A. Therefore here 1 is said to be the multiplicative identity in case of this. Inverse is A times A plus B is 0 is B plus A is the inverse property, where B is said to be inverse of A and A is said to be the inverse of B, or the additive inverse of B is how I understand. In general, B is always minus A. So minus A is said to be the additive inverse of A, is how I understand the concept of additive inverse. Similarly, when I take here A times B is equal to 1 is equal to B times A, that implies B is A inverse, written as A power minus 1, is said to be the inverse of A in the real number systems, provided here the condition is that A must not be equal to 0, because if A is equal to 0, the inverse of 0 does not exist. So I take the condition that A and B must be non-zero terms for multiplicative inverse, is how I understand the inverse property. Next, the distributive property states that A times B plus C is always A times B plus A times C, and this is only one exclusive property which includes two binary operations, addition and multiplication. And this properties under addition and multiplication hold for any three numbers being real numbers, whether rational or irrational. The properties hold, as can be verified through some of the example values you can take and simplify to see whether the left hand side is equal to the right hand side. Can be verified. So exponents is one topic which we already discussed in the previous sessions in the lower classes. Let's revisit exponents because some of its properties are very important in understanding this topic. So revisiting exponents. What are exponents? What is it about the word exponent in mathematics? Exponents are those numbers which are expressed in power form. The most simple thing is that if I have, say, 8, I can write this as 2 power 3, which is called the exponent form of writing the number 8, is how we understand exponents. It's very simple that I can write this as 2 power 3, and therefore 8 expressed in exponent form is 2 raised to 3. So using the exponents and the base, I generally have exponent which is written in the form a raised to the value b. In this case, this is said to be the base and this is said to be the exponent, which makes me understand that exponent is nothing but the power form, the power. So this is the base and this is the exponent or power. We indirectly also sometimes refer to exponent as power, is what I understand exponent. So sometimes we need to find the importance of exponents in mathematical problems. So what is the significance of exponent in math life? Exponents help us in simplifying the values usually when multiplications are considered. Say for example, if my question is to find 16 times of 64 without actual multiplication. The actual multiplication would be quite easy if you take a calculator and type and you get the answer, or sometimes by just doing it with the multiplication process. But if my question was to find this without actual multiplication, then that would definitely include exponents connected to identifying the value of the multiplication, as out here 16 times of 64. So let's take this and see how I can do it without actually multiplying the two values. Now let me take the first value, which is 16, which can be written as 2 times 2 times 2 times 2, which gives me 2 power 4, 2 raised to 4. So 16 can be written as 2 power 4, and similarly I take the second value, which is 64, and this can be written as 2, 3, 4, 5, 6. I can write this 6 times so that I get this as 2 power 6. So in this case, my value 16 times of 64 indirectly can be written as 16, which is in exponent form as 2 power 4. So 2 power 4 in its exponent form, and 64 in its exponent form is 2 raised to 6. So I get this as 2 raised to 6. And therefore, this by law of index, the first law of index, a power m into a power n is a power m plus n. Therefore, this finally gives me 4 plus 6 is 2 raised to power 10, is what is the value I get when I multiply this with this. Now, this is called the exponential answer for the given problem. Now, how do I find the general value of this? It is simple that I take this 2 power 10 as 2 multiplied 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I take them definitely by taking 2 2's 4, 4 2's 8, 8 2's 16, 16 2's 32, 32 2's 64 times 2 128, 256, 512, 1024. So every time I double the value, what I get, whatever I get here, I double here, double, 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 double. So 10 times you double 2, finally I get 1024. Now this is strictly done without the actual multiplication. If my actual multiplication, let's see if I get the exact answer for verification through 64 times 16, 6 6 36, 4 1's 4, and 6, 4, 12. And this is exactly the same answer. This is by actual multiplication, and this is by exponential form. Is how we understand the significance of exponents in real life.